So, welcome back to our course on the fundamentals of attosecond science and technology, which we bring to you from IIT Madras and IIT Tirupati. We are now in the fifth module on measuring the shortest pulses, and we key in on the same textbooks as we have been doing so far, the books by Roulier, the book by Chang, and the book by Diels and Rudolph, and many thanks to Professor Trebino, who is in fact one of the pioneers in this aspects of femto and attosecond science, for his generous inputs and material. So, what we looked at in the previous lectures has been about second and third order autocorrelation. We stated the problem, we figured out the details of second and third order autocorrelation, and today we will be addressing this very important question of is autocorrelation enough or not, and if it is not enough, then what lies beyond and what are the issues, what are the solutions. So, let us take up that. So, we understood that essentially we need to figure out the spectral amplitude that or the spectral intensity S of omega and the spectral phase phi of omega, and we need to solve this problem to have a unique solution, right, which is when we uniquely characterize a pulse or do its metrology. But is this possible in 1D? This problem, as stated mathematically, is something we know does not solve for a unique solution in itself. So, we will have to look at higher dimensionalities and so on and so forth, right. I mean, trivially speaking, certain things even in the normal world may not be possible to do in a limited geometry. There may be certain maneuvers, there are certain maneuvers which one cannot do in a 2D flat line, which become possible in 3 dimensional if the same problem were to be cast in 3 dimensions, in 3-dimensional space or in the context of 3-dimensional space. So, this is one such example. Now, we understood the models for detector, how to model the detector mathematically, then how to introduce delay lines, how essentially we can spatially encode temporal information, right, keeping in mind that 300 micrometers is the distance light travels in a picosecond or 300 nanometers in a femtosecond. Cube corners, the Michelson interferometer playing an important role in interferometric measurements, the fact that the autocorrelation is the Fourier transform of the spectrum, and that we can do multiple orders of autocorrelation, first, second and even nth order and so on and so forth. What the first order autocorrelation data looks like a priori, right. That is, we discussed that. We looked at second order autocorrelators where an SHG crystal helps us produce the second order signal, and we can do an intensity autocorrelation of the second order by crossing these beams. Then a more full blown version of the second order autocorrelator where we use up to say this point, the setup is the same whether it is first order or second order, and it is essentially the SHG crystal which is placed at the overlapping region of the two beams, which produces, for example, from a red beam a blue signal beam which enables second order autocorrelation, and that in the case of second order autocorrelation we get such a data map and we are able to we are then able to figure out from the envelope of this scenario where two Gaussian or a Gaussian pulse has been used to perform second order autocorrelation, right. So, essentially recasting the problem statement in another way, since in a first order process or a linear process we do not essentially have access to an event shorter than the event itself we are trying to measure, we have really a problem that essentially tends to become unsolvable, whereas if we use optical nonlinearities like the second and higher orders, we inch our way towards the solution, right. So, if you do not have a detector or modulator that is fast compared to the pulse width, we cannot measure a pulse, the pulse intensity and phase with only linear measurements. We are forced to, or we need to think beyond, look beyond and think of using optical nonlinearities, right. In other words, in principle, autocorrelation up to the nth order, the first, which is plain vanilla linear autocorrelation, second the SHG based method, we also had a third harmonic based implementation, all the way up to nth order becomes doing successive higher orders of autocorrelation can in principle give us full knowledge of the electric fields, um, the complete description of the electric field in time eventually. But very high orders of autocorrelation are usually not possible because the pulse usually is never strong enough to generate signals from arbitrary orders of autocorrelation. Usually we can manage up to 3 orders fairly reliably in our laboratory, right. So, this was a recap of the previous lecture. Now, let us advance to today's class. So, welcome to lecture 7 of this module on the measurement of the shortest laser pulses in this course. Femtosecond pulses is what we are considering now, but the course itself, in the course itself we are concerning ourselves with the fundamentals of attosecond science and technology. So, in the previous lectures, we again, to add to our recap, we looked at the convolution process, which is also sometimes called the folding product, where we take the function of interest about which we wish to know something, which need not usually be well known to us, and we use a gating function g of t, which is the window function in this case. The window function scrolls over the function of interest or the unknown function f of t, in which are both signals in time, and then we compute the area under the overlapped region between the two functions, where the overlapped region of the two functions non-zero regions, so to say. If it is like this, then the convolutional integral is essentially the green area that is scrolling through in this sort of an animation. And an autocorrelation is a special case of a convolution of a function with itself, right. An autocorrelation of a square pulse with itself gives a triangular pulse, a Gaussian autocorrelated with itself gives another Gaussian, a secant hyperbolic autocorrelated with itself gives another secant hyperbolic. As a consequence, the FWHMs of the autocorrelated signal are linearly proportional to the FWHM of the pulse itself, right. So, now as again we saw earlier, the second order autocorrelation is done using a second harmonic crystal. Now, we discussed the fact sorry we discussed the fact that an intensity autocorrelation is also a gating process, owing to the fact that in an elementary sense, even in the case of linear autocorrelation, what we consider the signal is essentially the autocorrelation signal is essentially the product term of I of t times I of t minus tau. Since the pulses have normally a rising edge and a falling edge, right. Otherwise, they are not pulses. By definition, they have a rising and a falling edge. Never mind the fact that they are not always Gaussian. We just take a Gaussian here for simplicity. Then essentially the signal that we are interested in arises out of the overlap region, which is this yellow pulse region which we have here. So, intensity autocorrelation is non-zero only in the region where the pulses overlap. So, overlap is the key to this discussion. We saw this yesterday. So, the spectrogram of a typical waveform E of t essentially can be obtained by taking as in the sense of convolution a gating function g of t, okay, and rolling it over on the waveform E of t which is of interest. We understand that the waveform itself can even be chirped, right. So, its spectral content can vary with time, the instantaneous frequency can vary with time. If we roll the gating function over this using a delay variable tau, which is practically the delay line of the interferometer we are using to do the metrology, then essentially the overlap, the integral of the product of these two functions E of t and g of t minus tau for every value of tau which we measure, that is to say take this slice which is representative of the shape of the function about this window function which is nearly a square pulse. It may add a factor of amplification or positive or negative amplification, that really does not matter so long as it is consistent. Then the area under this curve, right, along with a spectral measurement will yield us a spectrogram essentially. Okay. So, we are going to exploit this very much going forward, because this is the next step after autocorrelation. We also looked briefly in the previous lecture about implementing a third order autocorrelation using a polarization gating, where we use a nonlinear medium with an appreciable chi3 value, that is the nonlinear susceptibility of the third order, and implemented this polarization gate where we essentially bring in a waveform E of t, put it through a polarizing element over here, polarize it in a particular direction, say vertical, and hold a polarization and on the path of the delayed beam, the gating, the equivalent of the gate beam, we rotate the polarization of the gate beam to 45 degrees with respect to the linear polarization axis of the other beam, which is essentially the waveform of interest, cross them in the nonlinear medium, and here have something like an analyzer, which in the absence of this beam with the 45 degree polarization would essentially have kicked all this incoming vertically polarized beam out, owing to the fact that this polarizer is crossed with respect to the direction of polarization of this waveform of interest. On the other hand, in the presence of this gating beam at an angle 45 degrees to that of the test beam, which is E of t, interacting in the nonlinear medium, which is of course the crucial thing, the Kerr medium, a certain amount of polarization component which is perpendicular to the initial direction of polarization is induced owing to the gating beam, and we can once again vary the value of tau, scrolling the gating pulse E of t minus tau over the waveform of interest to generate a third order autocorrelation signal, because this is a chi3 process, right. So, that is basically the notion of using polarization gating in order to perform third order autocorrelation. We can use in some instances a cross referencing beam if we have a known reference pulse and unknown pulse. As I said, this is applicable in scenarios where you take a primary laser, split a piece of that of the initial pulse into a reference pulse, put the other pulse through some process or a test object such as a plasma or something, then use this known gate to figure out the waveform of this unknown E of t by taking advantage of a nonlinear process. Here, instead of second harmonic generation, use a sum frequency generation process, right. So, one can again do intensity autocorrelation. Now, as we also looked at in particular the interferometric autocorrelation, this is now going back to linear interferometric autocorrelation, where it is fringe resolved or it is the so called coherent autocorrelation. The math involved for it, as I said, I am leaving that as an exercise for you to work this out based on the steps that I am showcasing in these slides. The math is not really as intimidating as the number of terms seem to indicate for us. It is essentially very you can say straightforward, in the sense that the measured intensity versus delay I a of t, remember we can only measure intensities and not fields, is essentially a product of this interference term about which we have learnt earlier, and the complex conjugate part, the term by term complex conjugation of this generates for us the measurable interferometric autocorrelation intensity I a 2 of tau, right, and then multiply out all these terms, right, just take up, roll up the sleeves and multiply out all these terms, and what we are left with is a constant term which is uninteresting, an intensity autocorrelation term which we already got earlier, which is not the fringe resolved autocorrelation term, and the sum of intensities weighted with the interferogram of E of t. So, this term involving E of t multiplying E star of t minus tau is the interferogram term. Okay. So, that is what leads us to, and that is kind of what leads us to the interferometric autocorrelation. If you have a second harmonic crystal in the overlap region, you also get an interferogram of the second harmonic, which we will do second order autocorrelation with. So, this is precisely what coherent autocorrelation is. So, fringe resolved autocorrelation is called coherent autocorrelation. Coherent autocorrelation is fringe resolved. Okay. Incoherent autocorrelation is not fringe resolved, it is just about the envelope functions. This is also called the field autocorrelation sometimes, and this is sometimes called the intensity autocorrelation, but I would prefer that we call it either fringe resolved versus intensity autocorrelation, or coherent versus incoherent way of doing autocorrelation. So, in the case of interferometric autocorrelation, we get these nice beautiful fringes, right. This is the intensity envelope. Remember, we had this earlier too when we showcased intensity autocorrelation. That is the overlap, that this intensity stands for the fact that the two pulses have overlapped in time. Okay. It is not as if they crisscrossed each other without meeting each other. So, they are having quite a handshake in this process, but within that there is a substructure which is the fringe resolution, or fringe resolution in the Michelson sense of the Michelson interferometer. Now, besides that, there is another very important aspect besides the fact that the shape, the signature of a good autocorrelation interferometric autocorrelation signal is that the amplitude of the southern half or the bottom piece of this interferometric autocorrelation, where the 0 is set by this offset factor. If this is 1 unit, then the whole autocorrelation is 8 units, okay, measured in these units. So, this essentially gives us a good indicator of the quality of the autocorrelation arrangement. But besides that, there is a very pertinent aspect to doing fringe resolved autocorrelation, and why that is something a practitioner must usually prefer. Okay. That is the following fact: in all my discussions so far, I have marked the horizontal axis as the delay time axis, but remember that the delay is produced by a mirror on wheels. So, this is moved back and forth in an interferometer, so that an incoming beam of pulses comes this way and it returns, reflects back and goes away. Now, in reality, what we have on the horizontal axis is not necessarily a time value, it is actually the position of this mirror along a z axis. So, if this is 0, the delay line would have moved in this direction, retracting the mirror and introducing a so called positive delay, or it would have moved in the other direction in coming closer to the other beam in terms of time delays, that causes it, let us say, a positive delay, and this can cause it, say, a negative delay depending on the geometry that we are using. So, what we have here is essentially distance. So, we could say that this is basically 10 micrometers, maybe 20 micrometers, right, on the horizontal axis. Could this be 10 micrometers? Let me check. Maybe we should make this like 5 micrometers and 10 micrometers, minus 5, minus 10. Now, if I have a truly unknown pulse, which is what you are encountered with in a lab, even if I am just interested in knowing the full width at half maximum of this pulse, which is approximately this window, right, I need to convert a distance scale into a time scale, right, simply using the fact that tau is 2L by the speed of light. So, the accuracy and the correctness with which I determine this tau depends upon how well I know L. Now, here is the problem. A pulse contains several cycles of the electric field. Now, cycle to cycle, let us say I am talking about a pulse with a central wavelength of 800 nanometers, right. This is 0.8 micrometers. Now, the point is, how much control do you have when this stage steps from this location to the next, to the next, to the next. I have idealized it here. I am saying, suppose I have a stage which steps with an accuracy which is supposed to take 50 nanometer steps. It is never exactly 50 nanometers, it could be 50, a plus or a minus, maybe 10 nanometers, and so on and so forth, right. So, the integrity of the horizontal scale, distance scale, which is in reality what we have in a laboratory, is entirely incumbent on the quality and the integrity of the stepping process of this micro or nano positioning stage, and all these systems are engineered, made, and they could have their own error and whatsoever. So, what do we need in order to fix this arbitrariness in this metrology problem? What we need to do is a calibration. Take two rulers, what we call centimetric scales. Take two of them, even from the same manufacturer, keep them side by side and try to match them in terms of all details. Well, maybe with a good ruler you might find that, at least to the best that we can see with the eye, they are well matched. But then a poorer piece of manufacturing could have given us two rulers which are not really identical. But what is to tell us that even if two rulers have matched rulings, even if two rulers have matched rulings, right. So, this is 0, 1, no 10, 20 and this is the millimeter scale. How do we know that this interval is indeed 1 millimeter, or how accurately do we know? It is a question of metrology. So, now in order to determine this, I need a finer scale. I need another scale where I take this interval and I am able to look at this interval through a magnifying glass, and I need a scale which could have broken down this interval into further a factor of 10, break this down. So, this is 1 millimeter. So, I need a scale where each of this is maybe 0.1 millimeter. It is exactly the same metrology problem. Instead of shorter time, I need shorter spatial interval, a much better measuring device, right. So, this is really again becoming a chicken and egg situation, as we call it. I need to rely on spatial metrology and look at these numbers. These are 50 nanometers, is a very small number. So, you need for this to achieve this kind of step size, the technology of a closed loop piezoelectric nano positioning stages. While cost is not maybe a consideration for a student in this course, certainly a question of calibration comes in. How do I calibrate the step size? I need maybe another device with a 1 nanometer say positioning accuracy, and they come in with all kinds of problems, right. How repeatably does it step with 50 micrometers, right. All these things. I may have a nano positioner which does this well when I bought it, when it was new. After a while, with some aging, is the step size still 50 nanometer? I need to keep calibrating this again and again, and it becomes an endless process, and also even if I do this, maybe even a painful one. But there is a beautiful solution to this problem. Look at this interferometric autocorrelation signal. There is something very basic we know. We know that a maximum in this fine structure occurs when we made two copies of the waveform. We know that this maximum occurs when the two pulses are best overlapped. The next maximum again occurs when there is the best overlap in terms of time between these two pulses. So, in other words, the 0 happened when they cancelled out each other and interfered destructively. What is the condition for constructive interference? The condition for constructive interference in such an interferometer is that the phase difference between the two interfering waves for constructive is some m times 2 pi. For destructive interference, it is m plus 1, right, times 2 pi, an odd integer, or m plus, okay, I should write it as m plus 1 times pi, not 2 pi, right. Okay, there is the right way to express this. Have I expressed this? No. Okay, the right way to express this is 2m plus 1 times pi, right. So, this is twice m times pi. Yeah. So, basically, if I go from one constructive interference situation to the next, I have done this by changing the phase, incrementally changing the phase by a factor of plus 2 pi, or in terms of distance by moving a distance of one wavelength lambda. So, compared to this maximum fringe, this is a motion of 2 of lambda by the stage. This is the motion of another lambda, a lambda, a lambda, a lambda. So, the beautiful thing is the process has calibrated itself, you see. So, in order to know the full width at half max, I just need to do the following. I need to go from here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, let us say 19. So, 19 fringes constitute my delta tau. Each one fringe, if I know the wavelength of the central wavelength of the laser, says 800 nanometers. If it is 800 nanometers, I know that one fringe would be 0.8 microns, or convert this to time 2.7 femtoseconds. So, 19 times 2.7 femtoseconds, okay, this is what, take it as 20, this is 54 femtoseconds, right, cycle to cycle. So, it is 54 femtoseconds is the delta t. So, divide that by the square root of 2 for a Gaussian pulse, divided by 1.4, the width of the pulse turns out to be about 40 femtoseconds. We can just read it off by fringe counting. That is the power of fringe resolved autocorrelation measurements of pulses. So, one should always look to do this. In fact, if I may say so, you can get away with a really not so great quality for a stage and still do fringe resolved autocorrelation, because the calibration is done by the fringes themselves. They are the best calibration, right. You can just make cook up your own delay stage. You could put it, you can stick a mirror or a retroreflector. You can actuate it even with a loudspeaker whose diaphragm moves. That's something we often do even in our lab, and make your own fringe counter, do fringe counting, right. So, that is really the key to doing good autocorrelation measurements.